Hi there, welcome back. This is lesson 5 in our unit 1, the atom. And today's lesson is called Atomic Spectra. So in the last video, we talked about electron configuration, excited versus ground state electrons, and how glow sticks glow. So in this video, we're going to talk about atomic spectra, what it is, chemistry of fireworks, and we're going to continue working on excited versus ground state electrons. So, with this picture, I want you to notice what is different. Okay, what difference do you see? So hopefully you would say something along the lines of this one on the left is your ground state, and the one on the right is your excited state. Now we know it's sulfur because both of them have 16 electrons. But what happened is that this blue electron got excited and moved up in energy level. So now instead of having 2, 8, and 6, the blue one is now in a different spot, so you get 2, 7, 7. Now, this is not stable, it does not last long. This blue electron does have to go back to completely fill that second shell. But ground state, excited state. Okay, so if we're talking about chemistry involved in lights, if we're talking about, neon lights or stuff like that, there are electric currents passing through the gases that excite the electrons and make each gas glow a specific color. So again, these color lights that you see is the light that's released after an excited electron is falling back to its ground state. So remember, here's your energy shell. So let me grab a different color. Here's your electron in its ground state. And then energy comes in, hits that electron, so then it jumps up a level. Now, it doesn't stay jumped up forever. It has to come back down, but when it comes back down, it releases light. So just a kind of background of the nature of light. Light is a part of the electromagnetic spectrum. So that's the radiant energy composed of gamma rays, X-rays, ultraviolet light, UV light, visible light, and all this other stuff. So we're talking about stuff kind of in that general area. And so sunlight and different light has different wavelengths, different frequencies. And depending on what it is, you can kind of look at the wavelength and the frequency. So the longer the wavelength, the lower the frequency. So the frequency kind of measures how often that wave appears, and the wavelength is the length between wave and wave. So if you have a wave like this, a wavelength would be from here all the way to there. Now let's say in the span of the iPad screen, the wave occurs twice. So the frequency would be 2 times. But if I had, and it has a pretty long wavelength. So if I was to look at, this blue wave, we can tell that the frequency is a lot higher because it happened so many more times, but the wavelength is so much shorter. So you either have a high frequency and a low wavelength, or a low frequency and a high wavelength. That's kind of a little bit of physics there for you. So generally speaking, the red colors have a lower frequency but a longer wavelength, and the blues and purples have a shorter wavelength. So things with long wavelength they have less energy, and things with shorter wavelength or higher frequencies have more energy. So if you're thinking about putting a string up and down, it takes low energy to kind of get it to look like this. But the quicker you move your string to get it into that crazy pattern, the more energy you need. Okay, so atomic spectra, this is a lot of kind of words. So let me just kind of break this down. So when atoms absorb energy, the electrons move to a higher energy level. And again, once they absorb, then they jump, so absorb, jump. And then they don't stay in that excited state forever. They have to come back down to their lower energy levels. When they come back down, they release that energy in the form of light. And so that is what the excitation fallback theory says. When an excited electron falls back down, it releases energy in the form of light. Okay. So one thing to add is that the excited state is an energy state of higher energy levels, and that's why it's farther and farther away from the nucleus. Electrons in the ground state are as close as they can be, and they're the lowest energy they can be. Again, the closer you are to the nucleus, the lower the energy. The farther away, the more energy you have. So, if we're talking about the atomic spectra, the energy that's absorbed has to equal the energy that gets released. So what comes in must go out. This energy, you can't lose or create this energy. It has to go somewhere. So whatever comes in has to come out. And so you can kind of measure this. So if you look at an emission spectrum, if we're looking at white light and you put the white light through a prism, it breaks it down into the different colors that make it up. So a prism will separate these colors based on their wavelength. Now an emission spectrum kind of does the same thing. So here's an example of helium. There's helium gas in that light. So when it is excited and the electric current is going through it and the electrons are getting excited and jumping up, falling back down and releasing energy in the form of light, you can kind of mark what specific wavelength come out. And so that's what these lines represent. Those are the wavelengths of colors that make up the hydrogen gas. So if we're looking at absorption, the lines represent those dark spots, all the wavelengths that are being absorbed. And because whatever gets absorbed equals whatever comes out or released or is emitted, these lines represent the wavelength that got released. So each element has their own specific pattern. So if you can look at this, I think this is pretty cool. Each one of these lines represents a wavelength that is being released. So each element has a different pattern. So you can say, and every pattern is unique. So you can just look at hydrogen and helium. They look completely different. Now, it's kind of like if you think about gel electrophoresis in living environment, or DNA, fingerprinting. Every element has their own specific pattern, and that pattern is specific to that element. So if we're looking at the emission spectrum, and that's kind of what we're looking at, you get these characteristic lines at specific wavelengths for specific elements. No two elements have the same pattern. So that these are like these fingerprints for these elements. That pattern is specific to that element and that element only. So a lot of the time, you'll get a picture like this, and you'll get a handful of questions. So let's kind of dive deep into figure out how to answer these questions. So the first question is, well, what elements are in the mixture? So our question is, well, looking at this, which of these elements, there could be multiple, are in the mixture? So what you have to do, every line in the mixture has to come from somewhere. So you take your pencil and you trace it and you're like, oh, well, that line comes from gas A. And you keep going, well, this line comes from D. This one comes from A. This one also comes from A. These two come from D. And this one comes from A. So we can say that elements, gases A and D, are in the mixture because all the lines match up. So these lines in B or these lines in C are nowhere to be found in the mixture, so B and D are not in the mixture because the lines are not there. In order for something to be in the mixture, every one of those lines needs to be in the mixture. Everything needs to be accounted for. So if one line doesn't match up, well, can't be that. So the next question is, describe in terms of both energy and electrons and energy states how the light represented by the spectral lines is produced. So when it says in terms of, your answer needs to have electrons and energy states. If your answer doesn't contain both of those things and how they relate to the answer, that answer will not be marked correct. So a simple answer could be, when the electrons return to a lower energy state, they release energy in the form of light. So here we have our answer, our term electron and energy state. And you have to do more than just state the answer, state that word. You have to explain how that word relates to what they're asking. So the electrons, excited electrons return to lower energy states as they release energy in the form of light. So I'm not a huge fan of memorizing answers. I like to kind of figure out how they get there. But this is the answer to almost every single one of these types of questions. Okay, again, going into glow sticks like we did in the last video, when the dyes get excited, electrons get excited, they jump up, they fall back down, they release energy in the form of light, and depending on the dyes, you get these different colors. Same thing with fireworks. So now, we talk about each element has its own specific pattern, and it releases its own specific color. So every element has a different color, so the different fireworks are just made up of different compounds containing different elements. And so this is a cool lab that's totally not safe to do in school, but it's a cool video. If you ever see rainbow fire, this is why. You have these salt solutions that the wood soaks in, and depending on the metal, gives you a different color flame. Again, each color is different for each element. So, and if you were to put any of these colors through a prism, you'd get those specific bands at those specific places. So if you wanted a green flame, that's barium. If you wanted a blue flame, any one of these, rainbow fire does exist because of these excited electrons. Okay. So again, just kind of to wrap everything up, let's look at this in more detail. So here is a firework, and we're going to look at this specific electron. So energy is coming into that electron, so that means the electron is being excited and is going to jump in energy level and get farther away from the nucleus. Now, that electron is now at a higher level, and it's in its excited state, but it left behind its spot where it belonged. Now, this electron does not stay excited forever. It has to fall back down and go into its original spot. When it falls back down, it releases energy in the form of light. So the energy that came in to push it up has to be released. It can't hold on to that energy. It has to get rid of it somehow, and it gets rid of it in the form of light. And so now the electron is back in the ground state, where it belongs, its lowest energy level. Okay, so let's wrap it up with this question. What elements are in the mixture? So hopefully you said element X and element A are in the mixture. Now, why? How do you know that? Okay, so you should have said, these little lines are coming in, element X and A are in the mixture because all their lines are in the mixture. So what elements are not? Let me get rid of my pen. what elements are not in the mixture. Now, why are those elements not in the mixture? So you should say D and Z are not in the mixture because not all the lines match up. And lastly, describe in terms of both electrons and energy states how the light represented by the spectral lines is produced. So you should have said, when excited electrons return to a lower energy state, they release energy in the form of light. So you need to have the term electron, you need to have the term energy state, you have to actually explain how they relate to your answer, and that's pretty much it. So that is it for this video. We'll spend more time going over questions like these. But this is also the last video in Unit 1, the atom. So stay tuned for review lessons, lesson videos that will come. And our next official lesson video will be part of Unit 2, which is the periodic table. Bye.